A kinetic penetrator strikes the turret nose at 1500 meters per second, but the multi-layered composite matrix absorbs the shock and stops the internal spalling. Inside this 62-ton hull, a digital data bus links the commander to the gunner, allowing two separate targets to be tracked and engaged simultaneously. Through the thermal imaging system, the thermal signature of an enemy tank appears instantly, guiding the main gun automatic stabilizer to lock onto the target. However, this massive combat capability demands a non-stop supply of fuel, burning over 8 gallons of fuel just to start the turbine engine. During the late Cold War, Western engineers abandoned the complex MBT-70 project, shifting focus toward a simplified platform designed around survivability and mass production. Designers replaced the traditional diesel engine with a compact gas turbine, sacrificing fuel economy to gain unmatched power density and instant cold weather starting. To counter advanced chemical energy warheads, the hull profile evolved with a radical 60-degree frontal slope, maximizing the line of sight thickness of the integrated armor. Early testing proved that compartmentalized ammunition storage with spring-loaded blowout panels could completely vent a catastrophic propellant explosion outward away from the crew. The M1A2 System Enhancement Package project spans 26 feet in length, organizing its internal volume into 3 distinct, isolated survivability compartments. By placing the heavy turret rings at dead center over the suspension, engineers distribute the massive weight evenly across 14 torsion bar stations. The center of gravity sits exceptionally low to the ground, preventing rollovers during high-speed technical maneuvers on steep 40-degree slopes. This geometry minimizes the vehicle's silhouetted area, making it a significantly harder target to detect visually at extended combat ranges. The outermost defense relies on a high-hardness steel outer shell designed to disrupt the structural integrity of incoming kinetic projectiles before impact. Behind the steel, a complex matrix of ceramic tiles and depleted uranium plates slides outward by 20 centimeters along its mounting rails for replacement. This depleted uranium matrix offers twice the density of standard, rolled, homogeneous steel, delivering extreme protection against heavy anti-tank guided missiles. Heavy structural bulkheads transfer the kinetic energy of an impact through the main hull rings, avoiding deformation of the internal crew capsule. Heavy rubber side skirts attached to the lower hull flank panels, detonating shaped charge threats early to protect the vulnerable road wheels. The AGT-1500 gas turbine draws ambient air through massive multi-stage air filters, compressing the airflow by a factor of 14 inside the high-pressure compressor stages. Liquid fuel mixes with this dense air inside the annular combustion chamber, generating a combustion gas stream that hits 1700 degrees Fahrenheit. This high-velocity gas exhaust spins the free power turbine shafts, producing 1500 gross horsepower to drive the main rear drive sprockets. The Allison X1100 hydromechanical transmission manages 4 forward gear ranges, shifting seamlessly under full load conditions without losing critical cross-country momentum. Cooling this thermal signature requires dual high-capacity radiator fans discharging massive volumes of cooled air upward to blend with the hot engine exhaust. An under-armor auxiliary power unit generates independent electrical energy, sustaining all digital combat systems without running the main fuel-hungry turbine engine. High-pressure hydraulic pumps drive the turret traverse mechanism, rotating the 20-ton combat turret through a full circle in less than 9 seconds. If hydraulic pressure fails, a manual mechanical backup crank allows the gunner to turn the turret frame by hand using mechanical reduction gearing. An overpressure NBC filtration system seals the inner crew compartment, forcing continuous purified air inside to to block chemical toxic gases and radioactive dust particulates. The heavy steel track assemblies utilize replaceable thick rubber track pads, reducing severe vibration loads on the hull to prolong internal electronic component lifespans. The M256 smoothbore gun locks its sliding breech block vertically to seal the chamber containing 51,000 pounds per square inch of combustion propellant pressure. Upon firing, the concentric hydraulic recoil cylinders stroke backward by 30 centimeters, absorbing the immense energy to stabilize the vehicle platform during target engagement. The M829 APFSDS round discards its three-piece aluminum sabot segments instantly upon muzzle exit, leaving only the dense depleted uranium dart flying toward the target. An integrated bore evacuator traps high-pressure residual gases inside its steel collar tank, venting them out the muzzle to prevent toxic fumes entering the open breech. The coaxial M240 machine gun aligns perfectly with the main gun axis, sharing the same target line of sight for suppressing close-range, soft infantry threats. The primary digital fire control computer collects atmospheric inputs from the roof sensor mast, adjusting the internal ballistic calculations 30 times every single second. A muzzle reference system projects an eye-safe laser beam to a small mirror at the barrel tip, measuring thermal warping of the steel gun tube instantly. Dual-axis gyroscopes isolate the gunner's primary sight mirrors from hull vibration, locking the optical path perfectly onto the coordinate point, despite heavy, bumpy movement. The laser rangefinder, SA, calculates target distance within an exact accuracy of 10 meters, updating the elevation servo actuators to lift the gun barrel automatically. The commander's independent thermal viewer rotates completely separate from the turret shell, executing an automated hunter-killer workflow to hand off targets to the gunner. Data analysis confirms this combined digital processing cuts total engagement response time by 40%, ensuring first-round destruction before enemy platforms can return accurate fire. 4 integrated crew stations divide the internal armor volume placement balances physical weight distribution while optimizing manual workspace inside the crowded compartment. The driver controls the vehicle from a semi-reclined seat beneath the front glacis plate, operating a motorcycle-style steering T-bar to direct the transmission valves. The loader stands upright on a non-rotating mesh floor, lifting 40-pound main gun shells manually from the armored ammunition locker behind his shoulder. The gunner remains seated below the commander, manipulating an electronic dual-grip control handle to point the primary stabilized optics directly toward designated armor targets. The commander oversees the entire combat crew platform, using the integrated tactical display monitoring, situational battlefield tracking maps fed by cooperative network data. The target acquisition engagement sequence initiates when the commander locates an opposing combat vehicle hull, pressing the override button to align the main turret. The gunner assumes final fine tracking control immediately via the primary optical sight interface, activating the laser rangefinder to transmit target distance to the computer. The loader clears the path of the heavy weapon breech, flipping the safety guard lever downward to complete the electrical firing circuit layout. The gunner depresses the dual-grip firing triggers, sending a high-voltage pulse to detonate the primer and instantly discharge the high-velocity kinetic round. The solid steel breech block drops automatically, extracting the spent combustible cartridge stub, dropping the hot metallic disc directly into the collection basket. A high power-to-weight ratio of 24 horsepower per ton allows rapid acceleration, reaching an operational cross-country speed of 30 miles per hour. 7 dual road wheel stations. On each hull flank, guide the heavy track chain, adapting dynamically to rocks to distribute ground pressure evenly. By reversing the rotation of opposite track paths, the hydromechanical transmission executes a pivot turn, spinning the entire vehicle hull around its central axis instantly. However, climbing deep vertical obstacles over 36 inches tall stresses the forward idler wheels, causing high mechanical risk of shedding a track link during combat. Within armored brigade combat teams, the M1A2 SEP functions as the heavy breakthrough hammer, leading coordinated all-arms formations through prepared enemy defensive lines. The inter-vehicular information system links individual tank data terminals via secure VHF radio signals, updating the tactical network map with real-time positional intelligence. When holding defensive sectors, Mather tanks organize into disciplined watch positions, alternating turret angles across a 90-degree sector to secure complete interlocking fields of fire. The high fuel demand limits operational range to under 260 miles, forcing armored columns to halt every few hours for critical refueling support. Decades of technical engineering upgrades have driven total combat weight from early 54 tons up to an immense 69 tons for modernized configurations. This severe weight expansion stresses the original torsion bars and hydraulic dampers, increasing maintenance frequencies for ground support workshops by 30%. Strategic transportability constraints, TACs, limit deployment operations as the heavy combat platform exceeds load capacity thresholds for common bridge structures worldwide. By balancing heavy composite armor protection with interconnected digital systems, the M1A2 Abrams remains the ultimate engineering expression of Cold War heavy breakthrough doctrine.